All right, you guys. So we've talked a good bit about vectors, and vectors can lead into this thing called relative motion. Now, what relative motion is it simply means the motion of one object relative to the motion of another. So I'm going to draw something up real quick for us to look at. Okay, so here we have two pictures of two different scenarios. In both of them, we have someone standing on the ground watching a train go by. In both situations, the train itself is going to the right at 15 meters per second. However, the person, you'll notice, is walking different ways. So the person is inside the train car carrying something, and in one, they're walking to the right, and in the other one, they're walking to the left. Where they're walking to the right, they would have a velocity of 1.2 meters per second to the right. Down here, they have a velocity to the left of 1.2 meters per second, which would be a negative 1.2 meters per second. So the velocity at which they're going, the relative motion, is going to be different in each scenario. So how about we call this velocity right here of the person inside, we'll consider that the velocity of, let's say it's a worker on a train, okay? So the velocity of the worker on the train in the first one is going to be positive 1.2 meters per second, and the velocity of the worker on the train in the second one is going to be negative 1.2 meters per second. Then we have the velocity of the train to the ground, okay? The velocity of the train to the ground, which is that positive 15 meters per second, and that's going to be the same for both of them. Okay, so we have the velocity of the worker to the train and the velocity of the train to the ground for both of these situations. What we want to know, though, is the velocity of the worker to the ground. So, like, what is the relative motion of the person in the cart to the person viewing them from down here? Because they're going to be going at different velocity according to both of these scenarios. So what we're looking for is the velocity, like I said, of the worker to the ground. Okay? How we're going to find that is that we're actually going to add these velocities together. So we're going to add the velocity of the worker in the train to the velocity of the train on the ground. So here we'll have 1.2 meters per second plus 15 meters per second. And down here, we'll have negative 1.2 meters per second plus 15 meters per second, okay? So in this first scenario, the velocity of the worker to the ground is going to be a positive 16.2 meters per second, okay? And for the next one, it's going to be a positive 18.3 meters per second. 13.8 meters per second. Okay? So we have the velocity of the worker to the ground of this first scenario at 16.2 meters per second, and the velocity of the worker to the ground in this scenario at 13.8 meters per second. So from there, let's try out an example together. Okay, so the situation we have here is we now have a worker who is climbing the train with a velocity of 0.2 meters per second. So this velocity of the worker to the train is going to be equal to 0.2 meters per second. And he's on a train that is coasting forward at 0.7 meters per second. All right? And what we want to find is the velocity of the worker relative to the ground. So this time, you'll notice that some stuff is in the y and some is in the x. So we need to break this up into x and y components, just like previously when we were talking about vectors and adding them. Okay, so for the worker to the train, their x component is going to be 0 meters per second. And the velocity of the worker to the train is going to have a y component of 0.2 meters per second. The velocity of the train to the ground is going to have an x component of 0.7 meters per second. And the velocity of the train to the ground is going to have a y component of 0 meters per second. And since we're asked to find the velocity of the worker to the ground, and we know from our previous example that that means we need to add these vectors together, we're going to have the x coordinates added together. So we'll start with the worker. We'll have 0 meters per second plus 0.7 meters per second, which means that our x component for this one is going to be 0.7 meters per second. Then we need to add together the y's. So for the y, we are going to have 0.2 meters per second plus 0 meters per second, which means that our y is going to be equal to 0.2 meters per second. Now we need to find out just how fast they're going. So that would be like finding the hypotenuse of the triangle. So we're still going to be able to use Pythagorean theorem here since we are adding two vectors and we have x and y coordinates. So we're going to do the square root of 0.7 meters per second squared plus 0.2 meters per second squared. Okay? Now, when we do that, we get a result of 0.73 meters per second. Okay? That's our magnitude of the vector, but we still need an angle. Now remember, when we have the x and the y, we are allowed to use tangent, which would be opposite over adjacent. And remember that our y is our opposite and our x is our adjacent. So theta is going to be equal to the inverse tangent of 0.2 meters per second divided by 0.7 meters per second. When we do that, it gives us a theta of 15.95 degrees. And we know that it's going to be north of east since both of these are in the positive direction. So we'll end up with an overall vector of the worker to the ground is equal to 0.73 meters per second, comma, 15.95 degrees north of east. And that is our final answer for this problem. Now, let's do another one together. It's going to get a little bit more complicated, okay? Okay, so you are riding in a boat whose speed relative to the water is 6.1 meters per second. The boat points at an angle of 25 degrees upstream on a river flowing at 1.4 meters per second. We are asked to find the velocity relative to the ground and to give our answers in terms of degrees upstream. So let's look at the picture here, okay? All right, you guys, this is the picture that goes with the question we were just talking about. We have the boat going at 25 degrees. We have the velocity of the boat to the water, the velocity of the boat to the ground, and the velocity of the water to the ground. Now, what do we know? Well, we were given that the velocity of the boat to the water is 6.1 meters per second. We were given that the velocity of the water to the ground was 1.4 meters per second, but it's pointing downstream. So that's going to be negative 1.4 meters per second. And we were given that theta is 25 degrees, okay? So what we are asked to find is the velocity of the boat to the ground. What we need to do is break up these vectors into their x and y components so that we can use them in order to look for this vector right here. All right, so let's start with the boat in reference to the water. Remember, we've got 25 degrees here, okay? So the velocity of the boat to the water and the x is going to be 6.1 cosine 25, and in the y direction, it's going to be 6.1 sine of 25. So our x component of this vector is 5.53 meters per second, and the y component is 2.58 meters per second. Next, we need to look at the components for the water to the ground. All right? It is only in the y direction, so we know that the y component is going to be the total of negative 1.4 meters per second. Now, to go in and solve for this, the velocity of the boat to the ground, we need to get the x and the y components of it. So its x component is going to be 5.53 meters per second, because the x for this one is 0. So all we're going to add to it is 0, which means that the x component is going to stay that. And then the y component is going to be 2.58 meters per second minus 1.4 meters per second. And that's going to give us a y component of 1.14 meters per second. Now, in order to get our magnitude for this vector, we're going to need to use the Pythagorean theorem. So we're going to take the square root of 5.53 meters per second squared plus 1.14 meters per second squared. Okay, when we do that, we are going to get a magnitude of 5.71 meters per second. All right, and then we're going to need to find the angle, okay? Since we have the x and the y components, we can use theta equals the inverse tangent of 1.14 divided by 5.53. And that is going to give us a theta of 11.65 degrees. And it said to do it in terms of upstream. So we'll say upstream. Which means that overall, our velocity of the boat in reference to the ground is equal to 5.71 meters per second, comma, 11.65 degrees upstream. All right, now to leave you with the one we're going to do together in class tomorrow. The name of this one is called Flying to Cleveland. A wise pilot flying from Chicago to Cleveland plots a course that will take her directly to Cleveland. And we want to know in which direction does she fly the plane, and then how long does it take to reach Cleveland? Now you might be thinking, it sounds like there's a lot of information missing there. The information that you're going to need is in the picture that I am about to draw. So in this position, our pilot is starting in Chicago, which is considered 0 miles, flying to Cleveland, which is 300 miles away. The velocity of the plane in reference to the ground is 500 miles per hour, and the velocity of the air in reference to the ground is 50 miles per hour. So the air is actually pushing down on the plane at 50 miles per hour, which would cause it to move. So what we want to find is the velocity of the plane in reference to the air, Because in order for the plane to fly straight, it's going to need to fly at an angle, okay? I'm gonna leave you with as that you are going to need to find theta, and then from there, you can solve for how fast the plane is going. You can solve for its velocity. And then with that information, you can solve for how long it took them to fly there, okay? So you're going to need to use the following equation. The velocity of the plane to the ground is equal to the velocity of the plane to the air plus the velocity of the air to the ground, all right? Solve for theta. Then you're going to need to figure it all out from there. Just play around with it, see what you can or can't get. And we'll go over it in class tomorrow. So if you get confused, if you get lost, don't worry about it too much, but at least try, okay? I'll see you guys tomorrow, and I hope you have a great day.